Now the next equation I want to solve in fact is a wave equation, okay, but it's first order in time and first order in x. So it can be written as superposition of many waves. It has exact solution for I. Okay, so that's the exact solution. Plug it in. Okay, so if I want to solve it using finite difference, so again I do the time discretization like this. Now this is a wave, so it's not a good idea to put zeros at the ends. No, it's a good idea to put, the wave will move, so 0 will not remain 0. So one important, another boundary condition is called periodic boundary condition. So since it's a wave, just think that whatever the wave comes out comes back here. It's a very commonly used boundary condition in numerics, but also in physics. So if something is moving on a circle, it's a periodic. So there's a wave moving in a cylinder, so that will be a periodic wave. So you have to just think on those lines. Now let's do the time stepping of this. So again, please remember that I have I here, I plus 1, I minus 1, and so I am writing equation for one of the points, but I have n of these points, so I need to write for all of them. You have to be careful with the boundary condition. Only few things you have, one important point is boundary condition, you have to be careful. If you, at the same point, if you do from, periodic means this point is same as this point. So you shouldn't time step at both the points. Okay. Anyway, let's try to write down now equation for I. So d psi I dt of C. Now I can use Euler scheme for this first order. So I'll write this as psi I minus psi I minus 1 by h. Okay. So or let's make a better accurate scheme, psi I plus 1 minus psi 2h. Okay. So this central difference, so derivative at this point is psi I plus 1 minus psi I minus 1 by 2h. Happy? Now I time step. So psi I n plus 1 is psi I n minus c psi I plus 1 n minus psi I minus 1 n by 2h. Okay, so this is Euler explicit scheme. Now I am not sure whether I am communicating with you or not, but this is straightforward Euler explicit scheme, delta t. See delta t. Delta t has to be there. Okay. Now given time, given psi n, I can go to psi n plus 1 for every I. So that means I am got the values at next time step. Then next time step, I can go from t equal to 0 to t final. Now question is this scheme stable? Now stability you will find if you start solving it, you expect a wave, but you will not, wave will not come. Now it is very easy to check that this system is unstable. How do I check? I use the same idea. I try the function psi xt as ft dkx. Now look for ft. Ft should not blow up, or ft should not go plus minus plus minus. If I plug it in, so I will get, so shall I write the answer instead of doing the algebra? So this part you can do it yourself, and what comes out So for n, so I can write equation for f exactly what I did here, this one, this one. So this equation comes out to be fn plus 1 okay. So this is the equation for f. Now is f stable or unstable? Now you have to remember what we did for ODEs. Is this solution stable? Yes or no? Yes? Yeah? Why not? So modulus of this is greater than 1. Exactly like what I was trying to solve in one of the classes, minus I pi z. This was unstable for Euler explicit. The ideas are very simple, ideas are identical stuff, but here for f I get this, the mod of this is greater than 1, so it's unstable. So we are expecting a sine wave, but it will sine wave, but it will, the wave amplitude will keep growing. It's a moving wave, no? Like moving wave, it will just keep growing. So numerical scheme is not giving you the correct result. So we need to try to find another scheme which overcomes this problem. Okay, so that I will tell you in the next class. So we will again focus on this equation. We will try to solve it so that at least I get stability. Stability is critical, otherwise your solution is not well behaved. And then we will try to solve a fluid equation. Okay.